Okay, so in Wednesday's class, we talked about relative and absolute dating. Relative dating really relies on these six laws that I presented to you guys. There are two questions on the homework, which is over there on the left-hand side of the screen that dealt with this. They just ask you to put things in the order of events that they occurred, and that's what these six laws allow us to do, really. The first one is this law of original horizontality. That just says that sediment is deposited relatively horizontally as it settles either through the atmosphere, if it's kind of windblown dust, or most often if it's in water, the sediment is going to settle out and create these horizontal layers. The corollary there is that if you find non-horizontal layers, like are shown in this picture to the left, then they're probably disturbed or they've been uplifted and tilted. The second one was lateral continuity, and this just says that sediments or lava flows are going to be deposited horizontally, but they're going to extend continuously across whatever basin they're being deposited in until they either reach the edge of that, kind of like the side of a bathtub was the example I used in class, or if they thin out to nothing. So if you imagine pouring a bucket of sand into a swimming pool, it's not going to cover the entire bottom of the swimming pool. It's going to be deposited horizontally. It'll be thicker, right where you pour it, but it'll just thin out until it's nothing. So that's lateral continuity. And in between, where it's the thickest and the thinnest, it's more or less continuous. Okay, and then the law of superposition just says that in an undisturbed sequence of sedimentary rocks or lava flows, the oldest things are at the bottom and the youngest things are at the top. And that makes sense. One layer has to be there in order for the layers on top to have been deposited there on top. And so we went through this kind of little slide animation. Feel free to flip through these in the PowerPoints and just make sure that you understand these concepts are pretty straightforward. So this one, again, is pretty straightforward. It's just the law of inclusions, and it says that any rock that's included within another rock is older than the rock that it's included in, right? And so there's this nice conglomerate down here in the bottom, and it's just saying that each one of these, like this little light colored class here, or this dark one here with the arrow pointing to it, those are older than the whole rock itself, right? They are older rocks that were eroded, broken into little pieces, transported, and then deposited somewhere, and they formed a new rock, this new sedimentary rock. So that's makes sense. And this last one here, or the second to last, I think, is the law of cross-cutting relationships. This just says that anything that's cutting across another thing must be younger. So if there's a fracture in a rock, the fracture is younger than the rock itself, right? The rock must have been there in order to be fractured. That makes sense. This also applies to masses of magma. So these intrusive bodies of magma, they're going to be younger than the rocks that they intrude into. Okay, and so faults are one example of this, and we said, in this situation here, this package of rocks, limestone, sandstones, and shales, they're older than the fault. Right, the fault cuts through them, and so the fault must be younger. The soil on top and this erosional surface that it represents, that's younger than the fault, right? Because the fault doesn't go through it, right? The soil cuts across the fault, so it's the youngest. Okay, intrusions are another example of a cross-cutting relationship, and we made a point to talk about this zone of metamorphism here, contact metamorphism, that can give you an idea of whether or not these rocks were deposited around a body of granite, or if this body of granite was intruded into the rocks that surround it. Okay, and so the last part we talked about was unconformities. And an unconformity is just a surface that represents missing time. In general, that would be an erosional event, right? And so there are a few different situations we could have here, whether or not we're dealing with sedimentary rocks exclusively, or igneous rocks and sedimentary rocks. But in general, you deposit a bunch of rocks, then there's some erosion, right? So we deposit all the way up here, well past limestone B and shale A, but then we erode all those rocks down to shale A. Then we start depositing more rocks. And so this surface here is an unconformity. Excuse me. And so an unconformity can be what we would call a disconformity, and that has the rocks above and below parallel to one another. Or it could be an angular unconformity, and these happen a lot in the rock record. And in fact, there's multiple examples of them over here, right? This is an angular unconformity there. This is another angular unconformity there at the top, right? They occur a lot. But an angular unconformity is just one where the layers below are at an angular discordance to the ones above. That's what differentiates that. And it implies that there was some sort of some event where the rocks were tilted, right? Some mountain building or something like that, and then erosion, and then deposition of more rocks on top of it. Okay, a nonconformity is just one where there are igneous rocks underneath, and so it can kind of confuse. It could be confused with an intrusion, but we can identify the difference based on that zone of contact metamorphism again. And so there were a few examples. In this, A is obviously the oldest, and then B, and then C, and then D, and there are these erosional events in between. So we don't know exactly how much time is missing there, but it's clear from the nature of the surface itself, maybe these little pebbles at the base of the overlying formation. It's clear from the nature of the contact that it is indeed an unconformity of some kind. Okay. Similarly, over here we've got contact metamorphism on the A side of this, right? It's like kind of a fuzzy line, and so B must have intruded into A. So A would be the oldest, and then B, and then C cuts across both of them. So it's definitely the youngest, right? And so you can apply these rules and work through these slightly similar block diagrams or cross sections here. And then over on the homework, there's a slightly more complicated one. And so if you were to go about solving this problem here, you could start at the youngest or the oldest. And so, I mean, if we start at the youngest here, well, the youngest thing is this soil, F, right? It must be. This little creek cutting through F would be even younger, right? But F is the youngest thing with a letter. Then there's this erosional event R, right? And so R must be the next youngest thing, okay? Then we go into these rocks, and so in the youngest rocks there would be B, right? And these are at an angular discordance to the erosional surface and F, and so there must have been some event after the deposition of all of these rocks before this erosion where everything was tilted, some type of mountain building or some type of compressional stress resulting in folding or tilting of rocks. And so B would be the next youngest thing after R, and then K, and then N, right? Then there was this erosional surface, right? But the next youngest thing after this erosional surface is not J. It's not that layer of limestone J. It's actually this intrusion, because you can see that there's some contact metamorphism there, right? And so then you go back through J, D, and M, and so forth, right? And so you guys can work out the rest of that on your own. You could also go the opposite direction, right? It might be a little trickier at first to pick out what was the oldest, but you can work out which thing down in here is the oldest, and then go forward from there, either direction. And so there's that one, and then there's this Grand Canyon. These are the actual rocks in the Grand Canyon. So I'll record another video about absolute ages and half-lives and how radiometric dating works. But that should get you through that. Thanks.